In this lecture, we're going to do a hodgepodge of different exponential and logarithmic equations. Then we're going to end with some word problems, some applications. Our first example looks a little bit different than anything we've done before. It says the natural log of x squared equals the square of the natural log of x. Our usual strategy with logarithms on both sides doesn't apply here because the right side is squared. So we're going to take a different approach here. What I'm going to do is try to write everything in terms of the natural log of x. On the right side, I already have the natural log of x. On the left side, I want to rewrite this so that the input to the logarithm is just x, and we know we can do that using our rule that drags out the exponent. So I can rewrite this as 2 times the natural log of x equals the square of the natural log of x. And we haven't dealt with an equation like this in this chapter, but you've seen equations like this before. Let me replace each of those natural log of x's with a u. Then we would get the equation 2u equals u squared. So in terms of u, this is quadratic, and what you would normally do is get 0 on one side by subtracting. I'm going to do the same thing in our problem. I'm going to subtract 2 times the natural log of x from both sides to get 0 on one side. Now what would we do next in this equation with the u's in it? Well, we would factor. We'd factor out a u from each term. I'm going to do the same thing in our equation, except I'm going to factor out the natural log of x. When I factor the natural log of x from the natural log of x squared, it leaves behind the natural log of x. And when I factor out the natural log of x from negative 2 times the natural log of x, it leaves behind a minus 2. You can see the equations are essentially the same, except every place where I have a natural log of x in the original equation, I have a u over here. I don't think we need the analogy anymore, but we'll just do the last step. We would set each factor equal to 0 and then solve the resulting equations. So we would get u equals 0 or u equals 2. We're going to do the same thing here, but we're going to have an extra step. I get the natural log of x equals 0, or the natural log of x equals 2. But now I need to solve these for x, and I can do that by doing an algebraic rewrite. We can put this in exponential form. In the first equation, I get x equals e to the 0. Remember, the base of the natural logarithm is e, and so we get x equals 1. And on the right side, I get x equals e to the second power, which can't be simplified in any way. And so our two proposed solutions are x equals 1 and x equals e squared. We have to make sure that these are allowable inputs. We can plug 1 into both of these, and in fact, you get 0 equals 0 when you do that. You can also plug e squared into both of these because e squared is a positive number, and logarithms allow positive inputs. If you're looking for a general lesson from this problem, I guess one thing we can take from this is, if you're trying to solve an equation and you have no other ideas, see if you can get 0 on one side. Another thing that we did is we wrote everything in terms of the same expression. When we started the equation, we had a natural log of x squared and a natural log of x. It seemed like it would be easier if everything was in terms of the natural log of x, so we brought that exponent down so that we had some duplicate factors. That's what allowed us to factor in the following steps. Let's try another example that looks different. Here we have what we call nested logarithms. We have a logarithm inside of a logarithm. This says solve the common log of x equals 1. Here we do already have a strategy. It just looks different than anything we've done before. When we have the logarithm of an expression equal to a number, we've rewritten those in exponential form. So for example, if it said the log of u equals 1, well, we would write that in exponential form. U equals 10 to the first. I'm going to do the same thing here, but the thing inside of the logarithm is another log x. So the input log x goes by itself on one side. The base of the outer logarithm is the base of the exponential expression, and the output of the logarithm is the exponent. So we get that the log of x equals 10, and now we solve that by rewriting that in exponential form. The input to the logarithm is x, the base of the logarithm is again 10, and the output of the logarithmic expression is 10, that becomes the exponent, and so we get 10 to the 10th, which is a 1 followed by 10 zeros. That's 10 billion, by the way. The solution to this equation is 10 billion. Logarithmic functions grow very slowly, but the log of a log, nested logarithms, grow at an incredibly slow rate. I mean, look at this. Just to get an output of 1, you have to plug in 10 billion. This function doesn't reach a y-coordinate of 1 until the x value has gotten all the way out to 10 billion. Let's look at another equation that's different than anything we've done before. It says 10 to the 2x plus 10 to the x equals 42. What lessons did we learn from the first problem? Well, we learned it would be nice if we could write everything in terms of the same expression. Here we rewrote everything so it was in terms of the natural log of x. Here it would be nice if we could write everything in terms of 10 to the x, and we're able to do that because of a property of exponents that you're already very familiar with. Recall that a to the m raised to the n is a to the mn power. Reading that from right to left, it says if you have multiplication in your exponent, you can rewrite that as a power to a power. So I'm going to rewrite that first term as 10 to the x squared, and now both of my terms on the left are in terms of 10 to the x. How is that helpful? Well, this is now quadratic in terms of 10 to the x. Replace each of those 10 to the x's with a u. What would you do in this problem? Well, I think what you do is subtract 42, and then factor u plus 7, u minus 6, and go from there. That's exactly what I'm going to do here. I'm going to subtract 42 from both sides, get 10 to the x squared plus 10 to the x minus 42 equals 0. And then using this as my model, I know that I can factor this to 10 to the x plus 7 times 10 to the x minus 6, and that product has to be equal to 0. Check it quickly, you'll see that it works. 10 to the x times 10 to the x is 10 to the x squared, or 10 to the 2x if you add the exponents. On the outside we get negative 6 times 10 to the x. On the inside we get positive 7 times 10 to the x. So adding those together we get 1 times 10 to the x. And 7 times negative 6 is negative 42. Now we set each of those factors equal to 0. We want to move those constants to the other side so that we can rewrite this in logarithmic form. This is 10 to the x equals negative 7, 10 to the x equals positive 6. For the equation on the left, we get no solutions. It's been a while since we've talked about this, but remember that you can't raise a positive number to a real number power and expect to get a negative output. So there are no real solutions to the equation on the left. For the equation on the right, we just rewrite this in logarithmic form. The exponent becomes the output. The base of the exponential expression is the base of the logarithm, so this is the common log. And the output of the exponential expression becomes the input. So x equals the common log of 6. These exponential expressions have no domain restriction, so we don't really need to check to make sure that log of 6 is an allowable input. You can plug any numbers you want into an exponential expression. This next example is similar to this one, but at first it looks different. It says e to the x minus 20e to the minus x equals 1. What did we learn from the previous example? First thing you want to do is try to write everything in terms of the same expression. I have an e to the x and an e to the minus x. It would be nice if those were both e to the x, and I can rewrite the second expression as 20 over e to the x. Negative exponent will drag that down to the denominator. Now you might feel stuck, so here's where you might ask yourself what you would do if each of those e to the x's were u's. Oh, well, we usually clear out the denominators. We would multiply everything by u and get u squared minus 20 equals u. Then we would subtract that u to the other side because it's quadratic, so we want 0 on one side, and then we factor. This is u minus 5 times u plus 4. And we can proceed from there. I'm going to do the exact same thing here, but the role of u is played by e to the x in our equation. So I'm going to multiply everything by e to the x, and I get e to the x squared. That's also e to the 2x, but thinking of our last problem, it's probably better to think of this as e to the x squared minus 20 equals e to the x. Then we get 0 on one side, so we have e to the x squared minus e to the x minus 20 equals 0. And now we can factor this using our u example as a model. This is e to the x minus 5 times e to the x plus 4. In the first factor, e to the x minus 5 equals 0 means that e to the x equals 5. Taking the natural log of both sides, or rewriting this in logarithmic form, we get x equals the natural log of 5. On the right side, we have e to the x plus 4 equals 0, and I hope you can see that's not going to have any solutions. When we subtract, we get e to the x equals negative 4, which cannot happen, and so our only solution is the natural log of 5. So again, notice what our theme has been. In most of our examples, we found it helpful to rewrite everything in terms of the same expression, whether that be 10 to the x, e to the x, the natural log of x. That was our first step. Then we used a u substitution to help us see what we would do in an easier case, and we applied the same principles to our more complicated equation. Those are things that you can do in general, not just for exponential and logarithmic equations. We're going to end this lecture with a few word problems. This first example is something that we've done before, so I'm actually going to ask you to try this one on your own. It says a sum of money is invested at 3% compounded continuously. How long will it take for the account to double in size? Pause the video and see if you can do this. The model that we use for continuously compounded interest is A equals PE to the RT. A is the ending balance, P is the original investment, what we call the principal, R is the interest rate, T is the time in years. In this example, we aren't given a specific value of P. All we're told is that the account doubles in size. So the ending amount is twice the initial amount. A is equal to 2 times P. The interest rate is 0.03, and T is the question. So plugging all of these into our model, we get 2P equals P times e to the 0.03t. The goal is to solve for t, which means that we'd like to get this exponent down where we can work with it. Logarithms are the right idea if you try applying logarithms, but you've got to get the principal out of the way first. So we're going to divide both sides by p. And this step mathematically verifies something that you might have suspected was true. The size of the investment actually doesn't matter, because when we divide both sides by p, it cancels on both sides, and we get 2 equals e to the 0.03t. The doubling time is not dependent on the size of the investment. The only thing that really matters is the rate. How do we solve this? Well, we could rewrite this in logarithmic form, or we could take the natural log of both sides, which is kind of what we've been doing recently, so that's what I'm going to do. I'm going to take the natural log of the left side and get the natural log of 2. On the right side, we get the natural log of e to the 0.03t. Left side remains the natural log of 2. The right side, the natural log function and the exponential function with base e are inverses, so those cancel. And now we divide both sides by 0.03, and we get that t equals the natural log of 2 divided by 0.03. This is the exact answer, but to check to see if our answer is reasonable, I'm also going to throw this into the calculator and get a decimal approximation. So the natural log of 2 divided by 0.03 is around 23 years. Now I want you to notice that when interest is compounded continuously, the only thing that affects the doubling time is the interest rate. So if you wanted to find the doubling time at 4%, it would just be the natural log of 2 divided by 0.04. And if you wanted to find it at 10%, it would be the natural log of 2 divided by 0.1. When the interest is compounded a finite number of times, there are two things that will affect the doubling time. Here's an example of that. A sum of money is invested at 3% compounded monthly. How long will it take for the account to double in size? Here the interest rate is certainly going to matter, but so is the number of compounding periods. Recall that when interest is compounded a finite number of times, the formula is A equals P times 1 plus R over N to the NT power. Again, we're just told that a sum of money is invested, so we don't know what P is, but we know that the account's going to double in size. So A is equal to 2P, R is 0.03, N is 12 because we're compounding the interest monthly, and T is the question, how long will it take? We expect this answer to be a little bit bigger than the previous answer, although not by much. Plugging these in, we get 2P equals P times 1 plus 0.03 divided by 12 to the 12 times T power. We want to solve this for T, and so we're going to have to get that T out of the exponent. Here it's a little bit different because we don't have base E, but we've just learned how to solve equations like this, so we're just going to proceed from here. Let me write this on another slide and then we'll continue. I'd like to take the natural log of both sides so that I can bring this exponent down where I can work with it, but this P is getting in the way right now, so I'm going to divide that out of the way. Let me divide both sides by P. That will cancel on both sides, and we get that 2 equals 1 plus 0.03 divided by 12 to the 12t power. Now I take the natural log of both sides. The natural log of 2 equals the natural log of 1 plus 0.03 divided by 12 to the 12t. And the point behind this step is not to cancel the base. That doesn't work here because the base isn't e, but it allows me to bring the exponent down. So I get the natural log of 2 equals 12t times the natural log of 1 plus 0.03 divided by 12. And now to solve this for t, I just divide by everything that isn't t on the right side. To counterbalance that, I divide the left side by the same expression. And so our exact solution is that t equals the natural log of 2 divided by 12 times the natural log of 1 plus 0.03 divided by 12. Again, I want a decimal approximation for this. So I get the natural log of 2, close, divided by, parentheses, 12 times the natural log of 1 plus 0.03 divided by 12. And we see that it takes just slightly more time when you compound monthly. There's really not that much of a difference in this example between compounding continuously and compounding monthly. It does take a little bit longer, but it's still approximately 23 years. Let's do an example that isn't money. A lab starts with 100 bacteria in a culture and provides an environment so that the size of the culture triples every 5 hours. The model for the number of bacteria Q after t hours is Q equals 100 times 3 raised to the t over 5 power. How long will it take for the culture to reach 1 million bacteria? So in this example, we're given the model. We don't have to come up with the model. We were told what the equation is that relates the time to the number of bacteria. What we have to do is solve for one of the variables. The question is, how long will it take for the culture to reach 1 million bacteria? The number of bacteria in the culture is Q, so we're going to plug 1 million in for Q, and we're going to solve for T. So our equation is 1 million equals 100 times 3 to the t over 5 power. Let's write that on another slide. Pause the video and see if you can solve this equation. Use the previous example as a model if you think it will be helpful. Okay, we want to solve for a variable that's trapped in the exponent, so we're probably going to apply logarithms. Before we apply a logarithm, you want to get that coefficient out of the way, so I'm going to divide both sides by 100. 1 million divided by 100 is 10,000. 3 to the t over 5 power. I suppose we could rewrite this in logarithmic form using log base 3, but not all calculators can do log base 3, so the safer play is to just take the natural log of both sides, or the common log. Whatever logarithmic base your calculator can handle. On the left side we get the natural log of 10,000. On the right side we can bring the exponent down and we get t over 5 times the natural log of 3. You can solve for t all in one step, but I'm going to do this in two, just to be safe. First I'm going to multiply by 5. One of our standard ideas has been to multiply both sides by the denominator. That will cancel the denominators, and we get 5 times the natural log of 10,000. Which is not the natural log of 50,000. The 5 would come in as an exponent if you're going to put it inside the logarithm. So be careful about how you write that. Equals t times the natural log of 3. And now we divide by the natural log of 3. So we get t equals 5 times the natural log of 10,000 divided by the natural log of 3. Those natural logs do not cancel. Let's approximate this in the calculator. 5 times the natural log of 10,000 divided by the natural log of 3. It's going to take about 42 hours. So in 42 hours, or just under 2 days, the population will grow from 100 bacteria to 1 million bacteria. Let's do a model with a logarithm already in it. A computer algorithm is written such that the running time t in seconds is given by the function t of x equals log base 2 of 4x plus 3 plus 6, where x is the number of inputs. Approximately how many inputs would require a running time of 20 seconds? So in this function, you plug in the number of inputs to a computer program, to an algorithm, and it spits out how long it will take for the program to run. Whatever that program might be doing. Maybe this is a sorting program or something like that. The question here is, how many inputs would you need in order for this program to run for 20 seconds? So we know the time is 20. We're trying to solve for the number of inputs, which is x. So we're solving the equation 20 equals log base 2 of 4x plus 3 plus 6. Again, let's transfer this to another slide. We'd like to rewrite this in exponential form, but there's this stupid plus 6 in the way, so let's subtract that. We get 14 equals log base 2 of 4x plus 3. And now we write this in exponential form. The input to the logarithm goes by itself on one side. The base of the logarithm becomes the base of our exponential expression, and the output of the logarithm becomes the exponent. 2 to the 14th, I think, is 16,384. Let's check that. 2 to the 14th, 16,384. Yep, more proof that it didn't have friends in junior high. Subtract 3 from both sides. We get 4x equals 16,381. Divide by 4. And we get x equals 16,381 divided by 4. That is 4,095.25. Let's check that too. So 16,381 divided by 4. 4,095.25. Now the number of inputs needs to be a whole number. So the answer can't be 4,095.25. And I know your temptation is going to be to round this down because of the 0.25. But actually, if you round down, it's going to take less than 20 seconds, right? So we actually need to round up. The number of input that would require a running time of 20 seconds would be 4,096. So another way to say this is, if you have fewer than 4,096 inputs, then your running time is going to be less than 20 seconds. If you have 4,096 or more, then your running time is going to be more than 20 seconds. That's our last example in this hodgepodge lecture. We kind of jumped around a little bit between solving generic equations and solving specific applications. If you have questions about anything we did here or any practice problems if you tried, please reach out to me. You can see me in an office hour, or we can send emails back and forth.